Hi everyone, we are back and let's go ahead and look at Pset 5 solutions. So, fill out all the sections of the phase diagram, indicate congruent lengths. Alright, so let's just go ahead and fill out the phases first. Let's take it one question at a time. And I'm going to be a little bit lazy and do pluses. So this is going to be AU plus this region here, AU plus this. This will be this plus this, this plus this, this plus this, this plus this. This will be this plus beta, this plus alpha. And then, for example, the beta here, or actually beta here plus liquid, the gamma plus liquid. So you just kind of go like this plus liquid. This would be this little guy plus that little guy there in that section. Beta plus liquid. Let's go up. This plus this plus this. Again, this plus liquid here. Liquid plus this, liquid plus this, liquid plus this again, liquid plus this again. So again, you just draw the point here. You just draw kind of like a straight line. So liquid here plus this, and then this plus liquid right here. And there you go. So now I have to undo all this. But again, that's how you're going to do those phase diagrams. We've kind of gone over this quite a bit. I'm not going to write out all them in detail. But you just kind of draw that isotherm, that solid temperature. Do you hit a liquidus, do you hit a solidus, and add those regions. Indicate congruent melting points and invariant points. Label each invariant point. So what I'm going to do here, we know we have our bunny rabbit. So this could be either a eutectic, which I'm going to do circle, oid. Oid is, remember, eutectic is if there's basically, this would be a liquid to like an alpha plus beta. If it's a oid, there's only solids. So I'm going to do this as a square. And then a peri, which is just this or something like this, where we're going from basically here, an alpha plus a liquid to a beta right here. So two-phase region to single-phase region. Again, peri. I'm going to do a little star. And then peritectoid. Again, it would be only solids, so no liquid there. I'm going to do that as a triangle. So let's go ahead and let's try to find out. So I could see quite a few. So first of all, invariant melting point here, 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 here. Again, I'm going from pure liquid to pure solid right here. Those are my invariant melting points. Now, I've got I'm going to just do eutectics. Here's a eutectic, two-phase region, liquid to two-phase solid region, eutectic, and eutectic. So those are all of my ics, effectively. Now I'm going to go to my, let's see if there's any, I don't see any eutectoids. Those don't exist in this phase diagram. Peritectics, here, let's go ahead and count those out. Here's a peritectic right here. So it's a star, peritectic. Here's a peritectic, and I believe that represents and constitutes all of the peritectics, and I don't see any peritectoids in this diagram because you're just doing the solid lines here. So really, it's just the ics. So no peritectoids here. Somewhat of a boring one, but all right, let's go and zoom out. So we've got that. Consider a composition of 62% lanthanum at 400 C. What are the phases? And then let's get, okay. So 400 C, 62%. So it's going to be about, so let's say about right here. So let's say actually right here. What are the phases? It's going to be this phase, alpha, plus that phase here. So I see that that is at 50. So my basically alpha, and then my AuLa2, you can find this out chemically. That's going to be about 1, 2, 3, 4, 5, 6, so almost basically 67 composition. And then my composition there is at 62. So my C naught is equal to 62. So those are my phases. What is the composition in this alpha phase? 50%. What's the composition in the other phase? 67%. What are the fractions? So remember, if I want my fraction of alpha, I'm going to go in the opposite direction. So alpha is over here, so I'm going to do 67 minus 62 over 67 minus 50. So you see that that's a relatively small fraction. Why? Because I'm so much closer to this other phase. So fraction of AU LA2 is going to be equal to what? That's going to be, I'm going to go the opposite. So 62, oops, let me rewrite that. 62 minus 50 over 67 minus 50. So again, that's my lever rule. That's how I could find fractions. Compositions, you just go directly to the line. The composition in the alpha phase is this. The composition here is just that. All right. Relate the chemical potentials of each phase in the region. So if they're in a two-phase region, my chemical potential of alpha is equal to my chemical potential of AuLA2. So that's kind of, when we're in a two-phase region, our chemical potentials are equal. What are the degrees of freedom? Ooh, that's a good question. So if I'm right here, I have my degrees of freedom is equal to, so degrees of freedom, what is it? Minus composition equals phases plus 1, I believe, excuse me. So what are my components or compositions? Actually, let's remember the 2 came from, so in our Gibbs phase rule. So remember, where did the 2 come from previously? Because we can change both of those. So, and then here we go. Actually, here we go. My mistake right here. So it's not plus here. So remember, plus my phases equals components here. So what are my components here? This is always going to be 2 in a binary phase diagram. What are my number of phases? My number of phases in here are also 2, so my degrees of freedom is equal to 1. There we go. Excellent. Draw free energy. Oh no, I can't believe I asked you all this question, but let's go ahead and do it. Draw the free energy curves for the phase diagram at 1300 C. Explain the concept of a common tangent and what thermodynamic variable does it relate to. So remember, the common tangent is essentially describing the slope. So dg divided by, or partial derivative as a function of x the mole fraction, you could approximate that to my chemical potential. So remember, if I'm in a two-phase region, my chemical potentials are equal, thus I need to have the slopes be equal. And so that was actually nice on this one. So I'm going to go ahead and draw this up here. So I am right here. So let's go ahead and draw our, basically this is going to be our Gibbs phase rule. So I'm going to do, first I'm going to do liquid. So right now, my liquid is just hanging out and it's low here. So it's the lowest free energy curve. And then I want to draw, basically when I'm drawing these, I want the dashed lines where I intersect basically these regions, and then I'm going to have a single basically point right here. So those dashed lines are where my common tangents are going to occur. So this is going to be, my blue is my liquid. So blue is liquid, and then my other curve, effectively, is just going to be this beta. So my beta is going to come in here, and I'm going to have, basically, and actually I'm going to go ahead and draw the common tangents right now. Common tangents I'm going to just draw in gray. So I want the common tangents to look kind of like this, and then like this. So those are my common tangents. So my green curve is going to come in like this. So I'm going to come down. I am going to hit this point right here, and then I'm also going to hit this point basically over here. So I am pure liquid here. As you can see, I'm just always underneath it. But here I have a common tangent, and actually there's at that single point I'm a pure phase region. And then I'm going to also come up over here and hit this point, and then just go up continuously. Because as you can see here, I'm going to go down. So my liquid is going to be like this. Actually, it's going to go here. And then my liquid point will be also over here underneath it. So it's hard to kind of see this one, but I have a common tangent, common slope essentially at those points. So those are my common tangents. I could clean it up a little bit, but you can kind of, I could actually zoom in a little bit. Let's see. So for example, I can make, actually what I could do is I can make the green go up a little bit more. So for example, hit it up like this, and my blue, although again this is not drawing class, the key thing is getting those common tangents like this, and then for example I can go just right here and then touch and then go underneath it like that. But anyways, common slope right there. And that's it. So it makes sense, right? Pure liquid here because I'm below that curve, and then common slope where I'm in these two-phase regions right here. And then that's it. All right, let's go on to the next problem. So we need to do basically the same sets of problems. So I'm going to go ahead, change my pen. So again, what are the phases here? It's going to be this plus this. Phase here, this plus this. What's my phase here? It's going to be this plus the gamma. It's going to be this guy plus this guy. It's going to be this plus my gamma here. Gamma plus mg here. Mg plus liquid here. And then gamma plus liquid there. And then just tiny bit gamma plus liquid right there. What are my congruent melting points where I go from a pure solid to a liquid? I've got a couple here. Here, right here, and right here. So those would be my congruent melting points. What about my, do I see any eutectics around here? Yes, I do, eutectic. And then there's probably a super slight little eutectic right here, but I'm not going to count you off if you didn't hit that one. What about peritectics? So let's see, do you see any peritectics in here? I actually honestly don't see, again, I think that there's a little eutectic here. There actually must be, but I don't see any clear peritectics that kind of pop out at me. And actually, yeah, no, there's not any clear peritectics that jump out at me, but I can see here, what is this? This is Al plus this goes to another phase. That is a peritectoid. So I have a peritectoid here. What about here? I have single phase going to a two. This is a eutectoid. I don't even remember what that one is. So again, I'm seeing kind of like my bunny ears, kind of type of diagram. So eutectoid is a square. So actually I could see a eutectoid right here. So single phase solid region to a two-phase solid region of this and this. So there we go. And then we already got the eutectics over here. So those are my basically phase diagrams right there, all in a nutshell, or actually invariant points, excuse me. Composition of 32% Ma. So 32% Ma, and then what else? What temperature? 475. It's actually 450 here, so 475. Over here, and then 32 going up, so right here. So what are my, so right here. So what are my phases? They're liquid, they're Al. I ask for, chemical, so I know chemical potential of my liquid is equal to my chemical potential of my Al. I also know that my composition of liquid is equal to about, let's just call this, let's call it 35%. I know that my composition of Al is, let's call it, just for convenience, 15%. So my fraction of liquid, I'm going to go opposite, remember? So I'm going to go 32 minus 15 divided by 35 minus 15. My fraction of Al will be equal to what? Again, going close by, opposite, 35 minus 32 over 35 minus 15. So again, you see, Al is smaller. Why? Because I'm very close to that liquid phase. Makes sense, hopefully, to you. And then free energy curves at 300. This will be a little bit nastier, but we will kind of tackle it together. Oops. Actually, let me just kind of copy and see if I can delete all these here. Yeah, that's a lot easier. So I need to draw a phase diagram across here. So I'm going to just draw this kind of schematically here. Again, not looking for art, but single phase, all through here I need a two-phase region. Then a single phase here. And then I have another two-phase region here. Single phase region here. Two-phase region here. Single phase region here. Two-phase region here. And this is going to get a little bit nasty. But let's just kind of write it out. So here I am Al. This I am Al plus Al 3 Mg2. G2. Here I'm single phase region here. So basically what you're going to draw and what you're going to see here is I'm going to have basically this AL phase is going to go, so for example, I'm going to do this as my AL, I'm going to do this as my, this guy, I'm going to do this as this guy, I'm going to do this as this guy, and I'm going to do one more as, I should do this as the black guy. So, as we can see here from my red, I'm the lowest energy phase here, and then actually I'm going to do kind of my common tangent. So common tangent here, single phase here, I'm going to have a common tangent here, and then I'm going to have a common tangent, actually let's see, going down here, so common tangent here, common tangent here, leave that, we'll have a common tangent here, and then let me draw these lines a little bit more clear. So, common tangent, single, and then another common tangent here. So I'm going to hit those common tangent lines. So, let's get back. So I'm going to have a low curve here, and it's going to bounce up. And then I'm going to have my next curve, which will be the green one. It's going to come down here. I'm going to just sit here for a while, because this is my lowest energy state. And then I've got to hit this here, and then I'm going to get out of here. Then I'm going to bring in the blue guy, because it's going to come way over here, and then I just start to have the common tangent in this two-phase region here. I'm going to kind of hang out here, and then I'm going to get out of here, and then I'm going to bring in my little gray one, same thing. Hang out as a common tangent for a little bit. Now you're the lowest energy system. Hit here, get out of here, and then last one, last but not least, go over here, hit it here, and then now just hang out. And that's it. That would be my free body diagram. That would be my free energy curves for this system. All right. That is all I've got. So I will see you all next time, and study hard for the exam. If you have any questions, let me know. And then good luck. And then again, common tangent, same thing, chemical potential. So I'll see you all next time. Thanks. Bye.